Preventing algorithms from making unfair decisions, such as those resulting from discrimination, is an ongoing challenge. We can tackle this to some extent with statistical fairness measures, but these tend to leave out the impacts that algorithms can have once they're in use and interact with the world. Consider, for example, navigation algorithms. You wouldn't expect there to be any adverse consequences to using, say, Google Maps to drive from A to B, but even here there are choices, and as it turns out, the way they're used now actually increases the average time to destination in the places where this was tested. The reason is simple. Google Maps and similar algorithms will reroute you if there is a traffic jam on the highway. If it does so for enough drivers, you end up with traffic jams not on the highway, but on local roads running through neighborhoods. And traffic jams there take much longer to dissolve than if they're on a highway. So, as you can see, you end up with a worse traffic situation by rerouting drivers with algorithms. In the US, where this was investigated, that also usually means that you get more traffic in poorer neighborhoods, as those are closer to the highways. Not only does the travel time increase, the road safety in those places deteriorates. And there you see the adverse impact of an algorithm once it's running at scale and in interaction with the environment. Such impacts, in this case on indirect stakeholders, are often hard to predict. But that doesn't mean that we can't do anything about them. Changes to the algorithm, such that traffic gets rerouted less often, could solve this problem without any need for further action. In the end, this is also a design problem. That being said, solutions aren't always as simple as a small fix to the algorithm. Predictive policing algorithms are a good example of the difficulties that come with algorithms interacting with the environment. In such cases, the AI gives suggestions for where police officers should patrol to prevent crimes most effectively. Algorithms usually do so based on historical arrest data, so on where police has in the past apprehended criminals. The problems come in when the algorithm has to be updated using new arrest data. The new data will of course reflect that police officers were mostly in the areas suggested by the AI, and thus made more of their arrests in those locations. The AI will see this as a sign that most crimes occur in those places and suggest them again, and so on and so forth. A feedback loop between the suggestions of the algorithm and the arrest records fed into the AI has been set up, enlarging any original biases in the data. Those kinds of feedback loops are hard to spot using just statistical fairness measures, and you can end up in situations where statistically everything checks out, and your algorithm might be considered fair, but in practice there are still serious disparate impacts. That can happen with policing, where, for example, the accuracy of the algorithm becomes a self-fulfilling prophecy, making it look as if its prediction accuracy is evenly distributed over the city, but it can also happen without feedback loops in place. Algorithms that would decide whether applicants get a loan or not can be deemed perfectly fair in terms of, say, the probability of getting a loan per group or the true positive rates of the algorithm, but could still cause serious harm. That's because in the long term, what matters most is people who get loans they cannot afford. In other words, what matters is people who end up in debt because of the algorithm. You can meet lots of statistical fairness criteria, but if the defaults are concentrated in a single group, then using the algorithm still leads to increasing inequality. So, should we simply pick another statistical fairness measure and hope that that solves things? Not necessarily. If you look at the philosophical literature, there are more substantial definitions of fairness, such as from John Rawls's Justice as Fairness. He holds that we should aim to distribute benefits in such a way that the people who are worst off have the highest level of benefits. On such a definition, the trade-off between non-discrimination on statistical measures and accuracy of the algorithm becomes much harder. A less accurate algorithm might approve fewer loans, lowering the overall benefits resulting from banks. And so, some measure of inequality might be tolerated if it means that the poor are better off because of it. Such an idea isn't captured by statistical fairness measures, and in general, there is a discrepancy between the philosophical literature on just distributions and the computer science definitions of fairness. In short, don't blindly follow the statistical fairness measures. Consider the impacts, both from the interaction, but also on those worst off, and use that to arrive at a conclusion about the fairness of an algorithm.